Okay, welcome. This is 2.6 logarithmic functions. So in 2.5, we learned about exponential functions. Well, exponential functions have something called an inverse function. And that inverse function is called the logarithmic function. Now, students hate logs. I have no idea why. They make computing numbers easier. They make solving equations easier, but students refuse to use them. Maybe because they look weird. I'll never figure it out. Okay, but let's get into the definition of logarithmic functions. So down below, a logarithmic function is the equation f of x equals log base a of x, where the base of a is greater than 0 and the base of a can never be equal to 1. This defines a logarithmic function with base a. Okay, so the way we say this is we say log base a of x. That's how we pronounce the logarithmic function. Okay, the domain of a log is the set of all positive numbers, 0 to infinity. The range of a log is negative infinity to infinity. So I believe we do not graph logarithmic functions in here, but the graph of a log function, so I'll just put them here just to do it. So if I have y equals log base a of x, the graph of a log function always looks similar to this. Okay, and then we'll also do the graph of a natural log function, and that graph also looks like that. So you see how we never go to the other side of the axis because the domain is all positive numbers from 0 to infinity. And then you see where the range is negative infinity to infinity. That tail goes to negative infinity. That tail goes to positive infinity. So there it is. Like I said, I don't think we graphed them, but that's what the graphs look like. Okay, so more information on how to read a log. Y equals log base a of x is read as log base a of x. So going over that again. Y represents the exponent on a that yields x. So that being said, since these are inverses of each other, you can rearrange a log. So you can rearrange a log into an exponential function. And the way to do that is quite simple. One thing to notice is that the base of the log is the base of the exponential function. So when we rearrange a log to an exponential function, we take the base of a and raise it to the outside power of y. Now if you look over here, that becomes a to the y. And then after that, we set it equal to the inside number of x. We set it to the inside number of x, which is right over here. So you get x equals a to the y, or you could even write a to the y equals x, whichever you prefer. They both are the same. So let's go over that one more time. To go from log to exponential, you take the base of the log, raise it to the outside number of y, whatever that number is, that gives you a to the y. Then you set that equal to the inside number of the log, which here is x. So you get a to the y equals x. That's it. I think there's like a snail diagram that some people use, but I always forget how to draw that snail. But that's it. That's how you go from log to exponential. Now, what if we went the other way? Let's go from exponential back to logarithm. So once again, the base of the exponential is the same as the base of the log. So the one way to say this is that the a becomes the base, right? So what do I like to say? This one goes down. So the base a, I say, goes down. So it goes down to the base of the log. And then the outside number of x comes inside the log. So that becomes inside the log. So now we have log base a of x. Once again, base a went down, the x went in. And then the very last one is the exponent goes out, which means it goes to the outside of the equal sign. It goes outside of the log. So whenever you rearrange from exponential to logarithm, you're always down and out. Maybe that's why people don't like logs. They don't like to feel down and out. Maybe that's it. But let's go over that one more time. To go from exponential to logarithm, this base of a goes down, which means it comes over here on the log. This x goes inside the log, which is right here, giving me log base a of x. And then this exponent of y goes outside the log, which is here. So to go from exponential to log, you go down and out. Down and out. There you go. That's how you go back and forth. That's how you go from log to exponential, exponential to log. And of course, there's more practice below. But let's get into the definition of more logarithms. Okay. So next one is called log base 10 of x. This is called the common logarithm. And it's usually written as just the log of x. So what we say here is that if you see log x and you do not see a base there, that base is always known to be 10. So log of x is the same as log base 10 of x. But since 10 is the common base for the common log, we don't have to write it like this. We only have to write it as the log of x. That's it. Now, you would write that base in to convert from log to exponential, which you see right here. So on this one, we want to go from log to exponential. So here, y equals log of x. And we say, hey, there's no base shown on this log. How can I convert it to exponential? Well, what we have to notice is that this is the common log, which means you can just fit a little 10 in there. And then you can now rearrange from log to exponential, which means base 10 raised to the outside number of y, which is right over here on the right side, 10 to the y, equal to the inside number of x, which is right there. That's it. That's all. Okay, so once again, if no base is ever shown then it is understood that that base is always 10, right? Because here in America, we do stuff in base 10. Okay. Very interesting subject too. Look up base 10, base 5, base 8 mathematics. It's pretty cool and weird. All right. So that's the common log. Now we get into something called the natural log. The natural log has a base of e. The base of the natural log is the number e, which you see over here. Log base e of x. But we don't want to write it like that. That looks a little too complicated. So another way to rewrite the natural log is right here. Look at that. The natural log of x. Okay? And for the natural log, if you do not see a base, well, that base is always the number e. So I could rewrite this as the natural log base e of x. That's it. Natural log will always have a base of e. But we know that, so we don't have to write it like that. We just write it as the natural log of x. That's it. Okay. Now, converting from natural log to exponential. All right. So we want to go from natural log to exponential. And once again, we say, hey, this log doesn't have a base, which means you know that since it's the natural log, you can fit in a small little base of e there. And then we convert from log to exponential. And you take this little base of e, raise it to the outside number of y, which is right here. And then you set it equal to the inside number of x, which is right there. That's it. Nothing else to it. And remember, converting from exponential to log. So if you've given e to the y, right? If you're given e to the y, then this becomes the base. So it's still the same process. This goes down. It becomes the base over here. This x goes in, which is right here. And this exponent still goes out, which is right over here. Down, in, out. That's it. Even for the natural log. Okay. There you go. There's log functions, common log functions, natural log functions. Now let's play around with rewriting these equations. So, yeah, change the size of that. So write each equation in exponential form. So all we want to do is rearrange from log to exponential. That's it. So we take base of 4, raise it to the outside number of 2. I'll write that down. You get 4 squared, and then we set it equal to the inside number of the log, which is 16. That's it. Nothing else. Now, does that happen to be a true statement? Yes. That's it. That's all we wanted. Nothing more to it. B, again, practice. Base A, raise to the outside number of C. So that's A to the C. Set it equal to the inside number of B. There you go. That's it. Now that's not a true statement, but sure, if you plug numbers in for A, C, and B, it would be true. Here is just practicing rearranging from log to exponential. Okay. C. Add a pin. Ooh, look at that. Can I drag this pin over here? Yeah, there we go. Finally. Okay. So now we want to rearrange the natural log to exponential, and we say, hey, I don't see a base. Well, now we know that the base of the natural log is the number, e. So we have the base there. Now let's convert from natural log to exponential. We take base e, raise it to the outside number of d. That gives me e to the d, set it equal to the inside number of t. Done. That's it. That's all. That's going from log to exponential. Now, second example, let's go from exponential to logarithmic. Okay. So, cool. Okay, so converting this. All right, we start with the base, right? This base of 2 goes down. So right now I should have log base 2, and then this outside number, right? This outside number goes in. So now I have log base 2 of 1/8 equal to this exponent goes out. Log base 2 of 1/8 equal to -3. That's it. How do you check your work? Well, just convert it from log back to exponential. 2 raised to the -3 is right there, equal to 1/8, which is right there. It all checks out. Let's do it again. Here we go. We'll start with the base. This f goes down, so you get log base f. This w goes in, and this exponent, oops, this exponent goes out. Log base f of w equal to h. There you go. All right. So we do it again. This time we have a base of e, which means we get to use the natural log. You can use the natural log. So since e is the base, of course, that goes down. So you get natural log base e. This outside number goes in of 20.086 equal to this exponent, which goes out, 3. Now, since we know the base of the natural log is always e, we can just rewrite our answer as the natural log of 20.086. equal to 3. There you go. That's it. That's log to exponential, exponential to logarithm. Okay. And now we want a calculator to evaluate each of these expressions rounded to 4 decimal places. So let me go to my calculator, stop this sharing, there's me, and go to my calculator, there we go, beautiful. All right, and the first thing we have is the log, which is this first button right underneath the second button, right? Don't hit second though, oops, there you go. Hit log, and then type in 643, close parentheses. Enter. And we said to 4 decimal places, so this is going to equal, or approximately equal, 2.8082. All right. And then we want the natural log. So look, right below your log button is the natural log button. Hit the natural log button and type in 8946. 8946. Hit enter. And we get that this is approximately 9.09. And you can round, so you can make this 0.990 if you wanted to. All right. And then the next one is the log of 5/8. Well, I can say log fraction button 5/8. Hit enter. Or I can even say log 5/8. Hit enter. Same exact answer. So you get negative 0.2041. There it is. Okay, and if you're still looking at the notes, there is a little chart there, right? We have a little chart. I wonder if I can show it on here real fast. Stop share. Let me pull these up. Let's see. Yeah, look at that. Zoom in a bit. Okay. And then I can share that screen for the OneNote. And all we want to do is type these numbers into the log function. So this whole paragraph explains why logs are important. They take these exponentially large numbers and put them into a simpler format to deal with. And one of the best examples is earthquakes, right? An earthquake, think about it. They're like, oh man, California got hit by a 7.1 magnitude earthquake. You're like, okay, I know that's bad, but why is the number so low? Like, if you can shake a whole city, if you can shake a whole continent, then that earthquake has to be exponentially large. So 7.1 is just an easier number to work with, because in reality, that earthquake size is like 200,000 or 2 million, what do they measure? I think millimeters or something like that, like 200 million millimeters. And imagine saying that on the news. Oh, California got shook by a 200,000 million meter earthquake. That's not a unit, but sure. And then people are like, that's too much for me to handle. That's just way too big of a number. But then we say, you know what? They got hit by a 7.1 magnitude earthquake. And people start freaking out. They're like, oh, I hope everybody's okay. But the 200 million one, they're like, they got to deal with that on their own. I don't know what that is. 7.1, like, we send help. 200 million, we don't do anything. So logs put everything into perspective. They take exponentially large numbers, put them into a simpler format. So that's all we're going to do on this chart here. Use your calculator and type in the log of 1, the log of 10, the log of 100. And if we start doing that, let's see, I should get the log of 1 is 0, 1, 2, 3, 4, 5, 6, 7. So you see that we take 10 million, and the log of 10 million is just 7. That's honestly telling us how many zeros 10 million has. So something to think about. Hey, look at that. Oh, but I have to scroll on here in order for it to work. Maybe I can keep recording like this. Let's see. No, I like it better than the other one, but this works too. Okay. Stop share. Back to you, Robert. Thanks, Robert. There I am. Share, 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 share. There you go. This one's a little better because I get to manipulate it with my pen and all that good stuff. So, okay. So that's how logs work. They make your life easier, but students just still decide to ignore them. Whatever. Okay. So we are coming across some exponential properties, or logarithmic properties, sorry. So one thing we know is that, well, anything raised to the 0th is 1. That's an exponential property, which means if you convert that to a logarithm, this means that log base a of 1, no matter what the log base is, will always be 0. Yeah, it makes sense. Convert that from exponential to log, or convert that from log to exponential, and you get these statements. Same thing below. Anything raised to the first power is itself. Convert that to a log, and you get that log base a of a is always 1. So the log base a of a is always 1. So if the base matches the number of the log inside the log, the answer is always 1. All right. And those, of course, stem from exponential properties because they are inverses of each other. Okay. So this lovely box, basic properties of logarithms. So let's look at the first column. We just saw this one above. It says log base a of a is 1. So if the base is the same as the number inside the log, the number is always 1. Hence, that's why below log of 10 is 1. If there is no base shown on the log, we understand that that base is 10. And since this is 10, that is 10, this is why this log equals 1. Same thing with the third one below. Natural log of e is 1. Well, this is because we know the base of the natural log is e. If this base is e, if this number inside is e, then our answer is just 1. Simple as that. That's it. That's the first column. Here. The log base a of 1, no matter what the base is, the base can be whatever it wants, the log of 1 is always going to be 0. That's why common log of 1 is 0. That's why natural log of 1 is 0. Even if I wrote the base in, log base 10 of 1, still 0. Natural log base e of 1, still 0. No matter what the base is. Okay. More properties. Log base a of a to the x. All right. Well, log base a of x, what we see here is that since you have log base a of a, those will cancel to 1, and this will just leave you with the exponent of x. That's it. Simple as it gets. Here, log base 10 of 10 to the x, this log cancels and leaves you with x. Same thing here, natural log base e of e raised to the x, this log cancels and again leaves you with that exponent. So that's it for that. Now here's another property. If you have a raised to the log base a of x, so this is an exponential function raised to a log function. If this base a is the same as this base a, then this cancels and still leaves you with x. Same thing here. This is 10 log base 10 of x. These cancel and leave you with x. This is e raised to natural log e of x. This part cancels and again leaves you with x. So all of these lovely properties and more to come. Logs get crazy, just like exponents get crazy, right? Remember all those exponential rules? There's about the same exponential rules as there is logarithmic rules. Okay. So, from the above chart, let's go ahead and determine the value of these logs without the use of a calculator. So we start on the first one, log base 12 of 12. Now, which column does this look like? The base of the log is the same number, is the same as the number inside the log. So this looks exactly like this property here. So log base 12 of 12 is the same as log base a of a, which means all of this still gives me 1. That's our answer. Second one, natural log of e to the 5x plus 7. Natural log of e to the 5x plus 7. What column does this look like? This looks like the third column. This one looks just like that one, where I will rewrite this for you. This becomes natural log e of e to the 5x plus 7, which means that this part cancels, and all we are left with is this exponent of 5x plus 7. So, with that being said, using that property above, this just becomes 5x plus 7. That's it. And then C, e raised to the natural log of x squared plus 4. All right, this one looks like the fourth column. This one looks exactly like this one. E raised to the natural log of x. So this one, with that being said, is just going to equal the inside of this log x squared plus 4. That's it. That's using those log properties. Okay. Now, do you have to remember all those log properties? Sure, why not? Or you can type them in a calculator. All right. Another log property or log formula is, let's see, log base b of x. There we go. Okay. So let's say we are told to calculate a log. But if you have this blue calculator or an old graphing calculator, it does not allow you to type in log bases. It does not allow you to type in log bases. So if our calculator does not let us type in log bases, then in order to evaluate the log, we must use the change of base formula. And the change of base formula works as if you're given, let me zoom in, if you are given a log, so if you're given log base b of x, this can be converted into, ignore this one, this can be converted into the fraction log x over log b. So the log of x over log b. Or equivalent, it can also be converted into natural log x over natural log b. So that's all you have to do is separate it. You take log base b of x and you separate it into log of x over the log of b. That's it. So I will show you how change of base works down below. And if you have a graphing calculator, I will show you how to type in log bases if you have the right graphing calculator. But again, I'm going to get rid of the step. You don't want that there. Okay. There we go. Okay. Example 5. Evaluate each of the following using the change of base formula. Okay. So if we're going to use the change of base formula, you can start with A. The first thing I'm going to do is rewrite log base 5 of 625 using the change of base above. This becomes log of 625 over log of 5. That's it. That's by change of base. Log of 625 over the log of 5. Actually, let me rewrite all of these and then I'll show you how to use them in your calculator. This one becomes log of 12.5 over the log of 3. And this one becomes the log of 11 over 16 over the log of 2. Now let's go to our calculator. So stop share. Let's see. Stop share. There's me. Share screen. Calculator. Let's see. There we go. Okay. So we're going to type in the first one. Let's see. Okay. So we type in the first one. I'll start with my fraction button and I'll say log 625. Right, log 625 over log of 5. That's it. Enter. We get 4. Or even, if you don't have that fraction button, log 625 divide log of 5. Same thing. Okay, moving on to the next one. Log of 12.5 over log of 3. Go to 3 decimal places, sure. 2.299, or we're even doing 4 decimal places all day, so we can do 2.990. And then the last one is log of 11 over 16 over the log of 2. Negative 0.5406. There you go. Okay, or you could have typed this one as in 11 divide 16 divide log 2. There you go. Okay, stop share on that. And now, let me see if I can open my TI-84. There you are. Run as administrator. Yes, do stuff. Open calculator. Okay, perfect. And now, I'm not showing you anything. I'll go back to my screen, share screen, TI-84. Okay, so the log inputs were the same as my calculator. It was like log of 625 over the log of 5. But let's say you have an updated graphing calculator. You can go to your math section. You can go to your, where is it at? I think it's a number. So go over to the number and let's see. Round and round and round. Not there. Complex, maybe? It's somewhere. Or maybe mine doesn't have it. Way to go. Okay, let's see. Log. I don't see log anywhere. Let's see. Summation. Oh, there it is. So math, log base, hit enter, and watch the magic. Wow, it's waiting for a log base, and it's waiting for the inside of the log. So that log was log base 5, move over, of 625. Boom! My goodness, you do not need change of base, but that's if your calculator's updated. So there you go, and that would work the same. So again, math, scroll down, I'll scroll up, and right there, letter A, log base. Enter, and put your numbers in. 3 and 12.5, enter, there it is, 2.990. Life is good. Okay, perfect. I'm gonna pause for a second. Okay, these next examples, we need to solve these exponential equations, and the only way we're gonna do that is rearranging from exponential to logarithm. Rearranging from exponential to logarithm. So, let's go ahead and do this on A. We have 10 to the x equals 153. So remember, if we are rearranging from exponential to log, this base goes down. So we'll have log base 10. This number goes inside log base 10 of 153 equal to, this exponent goes out. So log base 10 of 153 equals x. Okay, and now all we have to do is compute this. So we will use change of base above. Actually, we don't even have to use change of base, because since this is log base 10, I can rewrite as the log of 153 equal to x. No change of base needed because this is the common logarithm. So now all I have to do in my calculator is hit the log button, type in 153, hit enter, and bam. You probably can't see that, but there you go. Boom. Just like that. Okay. I think it's at 4 decimal places, so this is 2.1847 equal to x. Okay. Let's do it again. B, this is the natural exponential function, e to the x, which means we will use the natural log. So we'll go from exponential to natural log, since it's the base of e. So this again, oops, this again goes down. So we'll have natural log base e. This number goes in natural log base e of 0.3059 equal to this exponent, which goes out, x. Okay, once again, on this one, no change of base needed because this is the natural log, which means I can rewrite this as the natural log of just 0.3059 and type that in my calculator. So all I have to do is hit natural log 0.3059, hit enter, and I'll get negative 1.1845 equal to x. So I hit the natural log on that. Okay. C. All right. This one's going to take some work. All right. So this one's 1.02 raised to the 4t equals 2. So let's convert from exponential to logarithm. So the base is 1.02. So we will use the log, not the natural log. So this will go down, which means I get log base 1.02 of this outside number, which goes in. Log base 1.02 of 2 equal to this exponent of 4t. Okay. So now, this part is now going to need the change of base. So let's go ahead and change of base that, and we should get log 2 over log of 1.02 equal to 4t. And now I will type the left side in my calculator, round to 4 decimal places, log 2 over log of 1.02, and I get 35.0028 equal to 4t. And now all I have to do to solve for t, divide by 4. Divide by 4. And we get 8.7507 equal to t. Perfect. Okay, cool. All right, so that's using change of base. That is calculating logs and log properties. Okay, let's keep going. We made it to the last page. where we learn more properties of logarithms. Yay, right? Yay. All right. So let's get into the first rule. Of course, the above says let m, n, and a all be positive real numbers where the base cannot be equal to 1 and p is any real number. So these are all terms we're just using in the definitions below. So don't worry too much about that. Okay. So first rule is the product rules for logs. I guess before we get into all of these, the reason we have these rules, these new properties, is to make log calculation a little easier. So these rules allow us to expand logs into multiple terms or condense logs into one single term, making their calculation easier. So that's what these rules are for. And the first rule is product rule. It says log base a of m times n can be expanded into log base a of m plus log base a of n. So the product of terms inside a log can be expanded into the sum of multiple logs. Since there's only 2 terms inside the log, we are able to expand it to 2 terms connected by addition. This is how product rule works. Now let's try an example. So let's say I have the log of x times y times z. This becomes log x plus log y plus log z. That's how that works. And remember that we can also work it backwards. I can take log x, log y, log z, and put it back into a single log of x, y, z. So these properties can be worked backwards. Okay, another one. Let's say I have log base 5, that's not a 5, log base 5 of 2x, y. I can make this log base 5 of 2 plus log base 5 of x plus log base 5 of y. That's how we do it. And then one more. Let's say I have log base 2 of x plus 1 times x plus 2. I can make this log base 2 of x plus 1 plus log base 2 of x plus 2. That's it. That's how the product rule works. Okay. Next is quotient rule. Okay. Quotient rule says if you have log base a of m over n, the quotient inside a log can be expanded to the subtraction of logs. So this is quotient to difference. Okay, so you can expand it to subtraction if you have a quotient inside. All right, so let's see how that works. Let's say I have, easy enough, log of x over y. Then this would be log x minus log y. Or log base, let's say, what's a good log base? I'll just make it log base 7 of, I can make this the last one, log base 7 of x plus 1 over x minus 2. Then this can expand to log base 7 of x plus 1 minus log base 7 of x minus 2. That's it. That's how that works. Next property is power rule. All right, this one's pretty straightforward. If you have log base a of some number raised to an exponent, p, then all power rule says is take this p and move it to the front. That's it. That's where we get this new term from. P times log base a of n. That's it. All the exponent does is come down. That's all. Okay. So let's try it out. Some examples. Let's say I did log of x squared. Then by power rule, this would be 2 log x. That's it. Let's say I had natural log of x plus 1 cubed. This would become 3 times the natural log of x plus 1. That's it. That power just comes down. That's how power rule works. And yes, all these rules work for logs and natural logs. So I could put a third property up here. I could say natural log of what? Let's say I just did 2x over y. This could become natural log 2x minus natural log y. There you go. Just to show you that it works for natural logs. Okay. The last rule is the equality property for logs. This one says, if on one side of the equation you have log base a of m, and on the other side of the equation you have log base a of n, then if the log bases are the same, you can set the exponents equal to each other. Not the exponents. The inside of the logs equal to each other. I was thinking exponents because exponents share the same thing. You remember? If you have a to the m equal a to the n, if the bases are the same, then m equals n. So you see why these are inverses of each other now. They share very similar properties. So let's say, for an example, I have log base 5 of x equal to log base 5 of 4. Since these bases are equal, this means that x equals 4. Or if I have natural log of 2 equal to natural log of x plus 2, since natural log has a base of e, since those bases are equal, this means 2 equals x plus 2. And of course, you would solve it after that. But that's how this equality property works. Okay. We're almost there, guys. Almost there. Okay. So let's put everything together. Everything we learned today, let's go ahead and solve these last 4 problems. Okay. So we will start with A. This says log base 3 of x plus 4 equal to 2. Our job is to solve for that little x inside the log. So this means that we have to get x plus 4 out of the log. And the only way to do that is to convert from log to exponential. So for this one, we take 3, raise it to the 2nd power. So you take 3 squared and set it equal to the inside of the log, which is x plus 4. Now, the log is gone. X is out there by himself, and all we have to do is solve for x. So clean this up, and we get 9 equals x plus 4. Subtract 4, and 5 equals x. That's it. That's all we had to do. Let's go to B. Okay. So now you have natural log e raised to the x squared minus 3x equal to 10. Well, we can use a property that we learned on the other page. Natural log of e. So remember that natural log base e of e is equal to 1. Also, natural log base e of e raised to the x is equal to x. This means natural log base e of e raised to the x squared minus 3x is going to be equal to x squared minus 3x. So this cancels and leaves us with x squared minus 3x equal to 10. So this was using properties we learned today. We now have a quadratic equation, which means we need 0 on one side. Take this 10, move it to the left. So I'll get x squared minus 3x minus 10 equal to 0. Factor. This should give me x minus 5, x plus 2 equal to 0. X squared, 2 minus 5, negative 3. There we go. That's an ugly 5. And we'll get x equals 5 and x equals negative 2. There we go. That's it. Okay. Next, C is going to be handled just like A. Okay. So we have log base 10 of x squared plus 5x plus 16 equal to 1. Our job is to solve for x, but we can't solve for x if it's trapped inside the log. So just like the one above it, convert from log to exponential. 10, raise it to the first. 10 to the first equal to the inside of the log. X squared plus 5x plus 16. Okay, we have converted from log to exponential. We have completely gotten rid of the log. So now all we have to do is solve for x. This is now a quadratic equation, which means we need 0 on one side. So we will rewrite this. First off, 10 to the first is just 10. So you get 10 equals x squared plus 5x plus 16. Subtract 10, subtract 10. We get 0 equals x squared plus 5x plus 6. Now factor, and we'll get 0 equals x plus, what do we have? 2, and x plus 3. X squared, 3, 2x, 5x, 6. Good. And this means that x equals -2 and x equals -3. Okay. So there is a little word of caution here. Since we have two values, we do want to check our work and see if they both work. So this means I would take -2 and plug it into the log. And then I would take -3 and plug it into the log. And we need to see if they're actually true. We didn't really have to do it on this one because it was just one solution. And that one solution should make it work. Here, we probably should have done it. You could have taken the 5, you take the -2 and plug them in. So I would say just double check your work and plug them in. I guess I'll do that over here since I have the time. All right, let me do this. I'm going to say check work. And we'll start when x equals -2. And all I have to do is say the log of -2 squared plus 5 times -2 plus 16. Clean that up. That becomes the log of 4 minus 10 plus 16. This gives me the log of -6 plus 16, which gives me the log of 10, which is definitely equal to 1. So that checks out. All right, so that's how you check your work. And you can plug in -3 and check it out as well. I think -3 would work. -3 would give me 9 plus 9 minus 15, which is -6. -6 plus 16 is 10. So yeah, so both of these solutions would work. Okay, cool. Just check your solutions if your homework asks to do so. See how happy I was to check my work. I knew it was right. Okay. Okay. So D log base b of x plus 2 plus log base b of x equal to log base b of 24. Okay, so our job is to solve for x, but in order to solve for x, I need to simplify the left side. This means that I need to combine it into one single log. So we are going to use one of the new rules we learned above. We are going to use the product rule, but work it backwards. Remember that if I have log base, not log base, just log of m times n, this becomes log of m plus log of n. So that's the product rule we learned above. So what we're going to do now is take log of m plus n and put it back into one single log. That's what we're going to do here. So all of this, log base b of x plus 2 plus log base b of x, if I work it backwards, I get log base b of x plus 2 times x. That's what this becomes. Log base b of x plus 2 times x. Still equal to log base b of 24. Okay, I'm going to rewrite this one more time because I don't like the x being there. So I'm going to make this log base b of x times x plus 2. And I'll even put little brackets here for neatness. And parentheses here. Why not? Let's be neat. Okay. Okay. So now, in order to solve for x, we're going to use another property. We're going to use the equality property. We see that these bases are exactly the same on both sides. So with that being said, since the bases are the same on both sides, we will use the equality property. So remember, the equality property from above is log base a of m equal to log base a of n. If the bases are the same, then m equals n. And that's what we're going to use over here. So since the bases are exactly the same, we're going to set x times x plus 2 equal to 24. So we get x times x plus 2 equal to 24. Distribute the x squared plus 2x equal to 24. We have another quadratic equation. So take this 24, subtract it to the left. This means you get x squared plus 2x minus 24 equal to 0. Factor, and you'll get x plus 6 times x minus 4 equal to 0. X squared, negative 4 plus 6, 2. Perfect. And my answers for x are x equals negative 6 and x equals 4. Okay, perfect. And of course, you could check your work and see if you are correct. But I believe it. Okay. All right. So that's it. Those are logs. They're just as crazy as exponents, maybe even crazier. But that's how you calculate logs. That's how you turn logs into exponents. That's how you turn exponents into logs. That is it. Bye, guys.